Hello and welcome back to this channel. Dear students, this is the revision lecture for the subject EFT. I will shortly explain some important tricks required for this subject. So do watch the video till the end. First part is boundary conditions. There are three boundary conditions. One is boundary condition between free space and conducting medium. Second, boundary conditions between two dielectric media. Third, magnetic boundary condition. You just have to remember one diagram. From this you can generate all the required diagrams. So in case of boundary conditions, there are two notations. One is normal component and another is tangential component. If I will consider the first boundary condition, that is boundary condition between free space and conductor, let us say lower medium is conductor, upper medium is free space. So as I mentioned, you need to memorize this only one diagram. Actually, normal component is perpendicular, vertical, horizontal component is tangential. So there are two parts. One is E, electric field intensity, another is D, that is electric flux density. So I mark this as a dt, tangential component of D, normal component of D. Similarly for E. Now for calculation of boundary conditions, you need to consider a closed surface 1, 2, 3, 4, 1 and a cylinder. Half portion of the cylinder is in one medium, remaining half portion is, in this case it is in the conductor, that is in the second medium. To apply the boundary condition, first for the calculation of tangential component, make use of the formula closed loop integration of E bar dot dl bar and use this surface. Then you will get the tangential component. To calculate the normal component, use the Gauss law. Formula is Q is closed surface integration of d bar dot ds bar. In all the derivations of boundary conditions, neglect the side surface area, consider only top and bottom surface area. If it is a conductor, in case of conductor, charges inside the conducting medium are 0. Another important clue for boundary condition is always for the path 2 to 3 and 4 to 1, values become 0 because they are in opposite direction. The direction is like this. So this is about the two electrical boundary conditions. One, as I mentioned, between free space and conductor. Second, you just make the changes in the names. So this is dielectric medium 1, second is dielectric medium 2. Another important change for this second derivation, boundary conditions between two dielectrics, is in case of first medium, mark this component as ET1. In second medium, mark this component as ET2. This formula remains same. And while doing the calculation, consider ET2 as negative. So as I mentioned, calculate tangential component using this formula, normal component using the Gauss law. Third boundary condition is the magnetic boundary conditions. Only notations are changed. In place of E, use H. In place of D, use B. That is the major change. And in electric field, we use this formula, closed loop integration of E bar dot dl bar is 0. In magnetic case, you need to make use of another formula. In place of E bar, write H bar dot dl bar. It is not 0, it is equals to current I. This is the only change. Rest all other things remain same. So this is as far as the boundary condition is concerned. Now another important concept related to this, related to this unit, is the types of capacitors. There are three types of capacitors. One is parallel plate capacitor. As the name indicates, there are two plates which are parallel to each other and medium between plates is a dielectric. Second is spherical capacitor. And third is cylindrical or coaxial capacitor. So you need to memorize the formula related to this for solving the numericals. For parallel plate capacitor, formula to calculate the value of capacitance, I am writing the formula to calculate the value of capacitance is epsilon A upon D. A is the area of plate, D is the distance between plates, whose values will be given in the question. Epsilon, throughout the subject, epsilon is expressed as epsilon 0, epsilon r. If medium is mentioned as free space, delete epsilon r, value of epsilon will become only epsilon 0. So this is the equation for parallel plate capacitor. For spherical capacitor, formula is 4 pi epsilon upon 1 by A minus 1 by B. A and B are the radii of inner sphere and outer sphere. In spherical capacitor, the diagram is like this. This is the inner sphere of radius A outer sphere of radius b, the gap between the two spheres is filled with the dielectric medium whose value is epsilon. So this is the formula to calculate the value of capacitance for spherical capacitor. One important concept related to this is b is the radius of outer sphere. If b is infinity, then 1 by infinity is 0. So it becomes, this equation becomes 4 pi epsilon upon 1 by a. That means 4 pi epsilon into a. This is known as isolated capacitor. Do remember this name? It is isolated capacitor. Third is the cylindrical capacitor. To calculate the value of capacitance for cylindrical capacitor, the formula is 2 pi epsilon L upon ln B by A. Do remember, ln is the natural log. That means this is expressed as log to the base e. Usually we take log to the base 10. In this case it is log to the base e. 2 pi epsilon L. L is the length of coaxial cable. B is the outer radius. A is the radius of inner cylinder. B is the radius of outer cylinder. So this is the formula to calculate the value of capacitance for the cylindrical capacitor. So these are the three important types of capacitors as far as the syllabus of EFT is concerned. Now the last part of this unit, I am talking about the unit which is related to boundary condition, is the energy stored. Stored energy is denoted by W to the base E. For solving the numericals, just remember only one single formula. It is given by 1/2 volume integration of epsilon E square dV. E will be given in the question. dV is differential volume. How to write expressions of volume? So if you are working in Cartesian coordinate system, see from the given specification, you can check which coordinate system is applicable. If x, y, z values are given, then it is Cartesian. Equation of dV is dx dy dz. If it is cylindrical, then in that case, equation of dV is r dr d phi dz. And if it is spherical system, equation is r square sine theta dr d theta d phi. In case of spherical coordinates, do remember limits of theta are 0 to pi, limits of phi are 0 to 2 pi while solving the numerical. So if you just memorize one formula and these expressions of dV, you will be in a position to solve the numericals related to the stored energy. So this was about the unit, about the chapter boundary conditions. Now the next chapter is Maxwell's equation. Very important part from this chapter is the set of Maxwell's equation. As I mentioned in earlier video also, you just have to remember only one set. All the required set can be generated from this set. So you just have to remember this set. There are two parts. One type is known as point form or differential form. Another is known as integral form. Very simple. If there is an integral sign, then it is integral form. So these are four equations, 1, 2, 3, 4. You should not change the numbering. I mean, equation 1 should be first equation only, second should be second, and so on. These are the four equations in point form. Similarly, remaining four equations are in the integral form. So as I mentioned, this is the set of Maxwell's equation for time varying fields. If the question is derive the expression for free space, then just you will have to remember two things. If you know this set, then apply the condition J bar is equals to 0, rho v is equals to 0. So wherever J bar is there, put 0, rho v becomes 0. This is first four equations. Similarly, I is, this is the common mistake. I is related to J. I is the current J bar, or J is the current density. So when J bar is 0, I is also 0. Then rho v becomes 0. That's it. You will generate the second set for free space. If it is asked to write the Maxwell's equations for conducting medium or conductor, the conditions are J bar is very greater than dabba d bar by dabba t, and second condition rho v is equals to 0. So to memorize, it's very simple. For free space it is 0. For conducting medium or conductor, J bar is very greater than dabba d bar by dabba t. Rho v in both cases is 0. So if you apply this condition, then in this case the second term gets vanished, only J bar remains. This term becomes 0. since J bar is very greater than delta T, only I will remain, this term become 0, rho V become 0. You will generate the next set, that is for the conducting medium. Last set, actually it is in the next unit, but last set is for harmonically varying fields. I mean Maxwell's equations for harmonically varying fields. To generate it, do remember simple trick, replace delta by delta T by J omega. Wherever B bar is there, put mu H bar. Wherever D bar is there, put epsilon E bar. Make these changes by using this basic formulae. You will be in a position to generate the Maxwell's equations for harmonically varying fields. Now the next part related to this unit, related to the unit of Maxwell's equations, is the concept of displacement current. For the short note, you need to draw a simple diagram. It consists of one resistor and one capacitor. I am talking about the concept of displacement current. So it is a simple circuit. It consists of one resistor and one capacitor. In case of resistor, the current directly passes through it. So this current is known as IC, which is known as conduction current. In case of capacitor, due to presence of dielectric, in between two plates there is a dielectric medium. Due to presence of dielectric, current cannot pass through the circuit, but due to the motion of displacement, current flows through the leads of capacitor. This current is denoted by ID. Now density of conduction current is denoted by Jc, density of displacement current is denoted by Jd. This is the concept of displacement current. For solving the numericals, you need to just memorize very simple equations. Conduction current is the normal current. It is given by V upon R. V is the voltage, R is the resistance. Its density is Jc, conduction current density, which is given by sigma into E. Sigma is the conductivity, E is electric field intensity. Then next equation is ID, that is displacement current. It is given by A d by dt of D. To calculate equation, to memorize formula for JD, displacement current density, skip this A from conduction current formula. So simple, it becomes d by dt of D. While solving these numericals on displacement current, one important condition everyone should know that IC by ID, that means ratio of conduction to the displacement current, which is same as ratio of JC by JD, that is conduction current to the displacement current, and it is given by sigma upon omega epsilon. If in the question it is mentioned calculate the frequency at which the IC and ID are equal, simply make use of this formula equated to 1, because when IC and ID are equal, this ratio becomes 1. From this calculate value of omega, and omega is 2 pi f. From this you will get the value of f. So you can easily solve numericals on displacement current just by memorizing this single formula, and of course these are also very simple formulae. So this is as far as the concept of displacement current is concerned. Last part from this unit is the most important point as far as electromagnetic subject is concerned, that is the derivation of Poynting theorem. So this derivation for electromagnetic subject is very important. Basic formula is P bar, that is power is given as E bar cross H bar. Cross product of electric field intensity and magnetic field intensity gives the value of P bar. I have already created the video on the derivation of Poynting theorem. Do watch that video. And for solving the numericals, you need to memorize one simple formula, that is average power of the Poynting theorem is given by E0 square. E0 is the amplitude or magnitude of E upon 2 eta. Eta is the intrinsic impedance. If it is free space, value of eta will be 377 ohm. So into S. S is the surface area. If the surface is circular, surface area is pi r square. So simply if you just memorize one formula, you can solve any type of numerical related to the Poynting theorem. Now the next part, next unit is uniform plane waves. At the starting there are two derivations as far as the syllabus of uniform plane wave is considered. So these are the derivations for free space and derivations for conductors. These derivations are based on Maxwell's equation. Just now I explained the Maxwell's equations. So apart from these derivations, you need to memorize two formulae to solve the numericals. Eta intrinsic impedance is given by under root of mu epsilon. And do remember, mu is given by mu 0 mu r. Mu 0 is permeability of free space. Mu r is relative permeability. Value of mu 0 you need to memorize. It is 4 pi into 10 raised to minus 7. Similarly, epsilon is given as epsilon 0 into epsilon r. Epsilon is permittivity. Epsilon r is relative permittivity. Epsilon 0 is permittivity of free space, which is 8.854 into 10 raised to minus 14. So this is the value of epsilon 0. So this is the equation for intrinsic impedance, and without fail, eta for free space is 377 ohm, or it is also given as 120 pi. Any value will do. This is the formula to calculate the value of eta. If free space is mentioned, do not calculate eta. Directly you can make use of this value. Next important parameter for uniform plane wave is velocity of propagation, which is given as omega upon beta. Beta is the phase shift. Omega is angular frequency, which is 2 pi f. Now remaining part from this unit is a depth of penetration. So this concept is again most important. I have already created the video on this concept, that is concept of depth of penetration. It is also called skin depth. The notation is delta. So do watch that derivation. It's a pretty simple derivation. For solving the numericals, for good conductors, do remember these values. Delta is 1 by alpha, which is same as 1 by beta, and for good conductor, formula of delta is under root of 2 upon omega mu sigma. Omega is 2 pi f, mu is mu 0 mu r permeability, sigma is conductivity, whose values will be given in the question. Then again you need to memorize few more formulae. We know that Vp is basic formula is omega by beta, and 1 by beta is delta, so it can be written as omega into delta. So this is formula of velocity of propagation in terms of delta. Then basic formula of lambda, wavelength is 2 pi upon beta, but 1 by beta is delta, therefore lambda becomes 2 pi into delta. So by making use of this formula, you can solve any type of numerical related to the uniform plane wave. Now remaining part from the chapter of uniform plane wave is the reflection coefficient. There are 4 formulae if you want to solve numericals on reflection coefficient. I will tell you the trick how to memorize those formulae. One is reflection coefficient. It is ER upon EI. E stands for electric field. ER is reflected electric field. EI is incident electric field. This formula is eta 2 minus eta 1 upon eta 2 plus eta 1. Second formula, transmission coefficient, it is given by ET upon EI, and the formula is 2 eta 2 upon eta 2 plus eta 1. Eta 2 plus eta 1. This is the formula of transmission coefficient in terms of E bar. Now, if you just remember these two formulae, one more formula, that is reflection coefficient for H bar. Simply write it as HR upon HR. What I did, I just made the changes in the notations. And this is the second set. Remember it like this. It's not a technical thing. I'm telling you the tricks how to memorize it. It is eta 2 minus eta 1. For the second set, just interchange the positions. Write it as eta 1 minus eta 2 divided by, numerator remains same, eta 2 plus eta 1. Then TT. From this formula you can well write HT upon HI. This is equation of transmission coefficient for H bar. Here in earlier equation we had 2 eta 2. Now this becomes 2 eta 1 divided by eta 2 plus eta 1. These are the 4 formulae. If you know these 4 formulae, you can solve any numericals related to reflection coefficient. How to memorize this formula? I have already told you. One more simple trick. Every denominator has eta 2 plus eta 1. Only numerators are different. In first case, it is eta 2 minus eta 1. Here, it is reverse, eta 1 minus eta 2. In case of TT, transmission coefficient, it is 2 eta 2. Here, it is 2 eta 1. So if you apply these simple tricks, you will be in a position to solve the numericals related to uniform plane wave. Now the last part is the transmission lines. As far as the transmission lines are concerned, you need to learn how to solve numericals on the Smith chart. I have already created 4 videos, 4 different types of numericals are covered. If you already watched those videos, just refresh the concepts, because Smith chart is an important part of electromagnetics. Apart from this, as far as transmission line parameters are concerned, for solving the numerical, you need to memorize just 2 formulae. Z0, formula of Z0, that is characteristics impedance, which is given as R plus J omega L upon G plus J omega C. R is resistance, L is inductance, G is conductance, C is capacitance, and next parameter gamma, that is propagation coefficient, propagation constant, is given as R plus J omega L into G plus J omega C. So if you know this formulae, the 2 formulae, you will be in a position to solve the numericals on the transmission line. Then one last concept related to transmission line, which I feel it is required, is the condition for distortion-less transmission line. This condition is LG is equals to RC. So if you maintain this condition, then there won't be any distortions in the transmission lines. Dear students, this was the quick review of the subject electromagnetic field theory. I hope you might have understood the concept, because I have already created separate videos on each and every part. In case of any difficulties, you can well watch those videos, and if you like such type of videos, do let me in the comment section, so that I can create similar videos of revision for other subjects also. Thank you very much.